Okay, let me just re-intro since I'm recording now. Today we're going over concurrency in Rust. We're going over why we use it, why it can be hard. We're going over some ways to actually implement it with threads and communicating between threads. Additionally, before we get started, we're going to be doing a little bit of course announcements. So today is the second to last lecture. It's really basically the last kind of heavy content lecture that we're going to be having. Next Tuesday, the final lecture is going to be a little bit more focused on just kind of maybe some more general stuff, and we'll be giving out kind of lots of extra credit over that next week. In one maybe specific way that you can earn some extra credit, and a lot of it is by filling out the feedback form that we're going to be posting probably later tonight, potentially tomorrow. Um, we're still hashing out some of the details on how we want to allow it to be anonymous versus also being able to know that people filled it out and to give you extra credit. And obviously, we need to know who that is. And so we're kind of working out the details with that, but we should get that done pretty soon. And so you should see that feedback form coming to you in the near future. It's super helpful to fill those feedback forms out. It helps us improve the class a lot. Basically, every single semester this class goes through some really massive changes. And so, by always kind of evolving and taking in the student feedback, we're able to kind of keep this class great. Um, and so definitely give us some feedback, right? We already have a lot of stuff that we know we want to work on, maybe certain homeworks that we want to change and things like that. But hearing it from you as well will help us a lot, as well as the fact that doing this online is always an interesting challenge, and so there's a lot of stuff that maybe we should improve there. So, let us know all of that. Let us know your thoughts in the feedback form. We always love to read it and to improve and build the class up on your feedback and make it better for all the students who are going to take this in the future. Um, okay, so without further ado, we'll actually start kind of talking about the content. So let's kind of introduce this idea of concurrency at first. We've talked a little bit about Rust, and we've talked about kind of this idea of ownership and borrowing a pretty good amount actually, and why it can kind of be useful. And today we're going to be really exploring one of the applications that makes Rust concurrency and Rust, excuse me, that makes Rust borrowing and Rust ownership kind of such a great feature, and what makes it maybe so valuable as a feature for a program. So concurrency is the ability for a program to be split up into different parts that can each run independently of each other. And ideally, we're actually running these at the same time if they can be. And so, we're going to be kind of calling something that isn't concurrency, we're going to be calling parallelism concurrency. But this is really the idea that I want you all to have is, so concurrent but not parallel execution means, you can break your program into different pieces, maybe, different functions that are called. And, this thread, this CPU core, this process, or really it's a thread, handles this piece, and then this piece, and then this one handles this one handles this piece, and so on and so forth, right? And really, one of the amazing strengths of concurrency and parallelism, the ability to break these parts up, allows us to very often run them at the same time. And so, hopefully you can see that this top program is going to finish in, what is this, 3 times as long as this bottom program. And so, being able to get a 3 times speed up in your code is kind of a big deal, especially if you can do it, hopefully easily. So, why are we actually using concurrency? Now, I'm actually an ECE major myself, and so this is maybe a fun little interjection is, we've made CPUs as good as we can make them for the developers. We're kind of starting to hit a limit. And so, you can see here when we talk about how fast your CPU is running, the frequency, how many operations it can do per second, we're starting to level out, right? We're kind of hitting a hard limit because if we continue to increase it, the CPU will catch on fire and bad things happen. And so instead, we focus on increasing the number of cores. And the number of cores is really this same idea of how many different workers you can have doing different things at the same time. right? And so, as a programmer, one of the major kind of focuses that we're going to be seeing over the next, 10, 15, 20, 30 years is going to be, making sure that you're writing efficient and parallelizable code, and that, when you're implementing these things, you're implementing them in a way so that they can run quickly on multiple cores at the same time. And so learning about parallelism is really kind of the key point in how we actually do this, right? Parallelism is kind of the cornerstone on how things like GPUs, graphic processing units, work, and really how a lot of like many more interesting concepts are built over and enabled by parallelization. So let's talk a little bit about this. Concurrency enables us to take advantage of these multiple processor cores in computers to run our code more quickly, or even sometimes to be able to run our code in something that is not an infinite amount of time. So, what's the catch, right? Why isn't everything parallel ever? It's not necessarily easy. And especially in a lot of other languages, when we look at C, when we look at C++, Java, Python, you can actually run into some really tricky bugs with concurrency. And luckily, Rust makes it pretty easy, or at least covers a lot of our bases with this idea of ownership. But let's maybe well, first, let's look at maybe a more concrete example. So this is Firefox's code base, which is written in C++, which makes it maybe a little bit harder to do concurrency. And then, of course, Firefox is millions of lines of code of C++, and so they have this bug to parallelize CSS selector matching. Maybe you remember, your CSS selectors. To be able to do that in parallel would obviously have a pretty concrete speed up in Firefox. Every single page you load pretty much has CSS that's running on it, and this is going to be happening very often. So, this, however, because it's millions of lines of code, and parallelism and concurrency can be pretty hard to implement. This bug has been sitting here for 7 years. It's probably more now. I think this is actually pretty old, so it's probably more than 7 years old. And it's because it's not necessarily easy to do these things all the time. Now, the other side is, it's actually a huge speed up, and so we can see some, loading time speed ups. We have Amazon, implemented concurrency. Yeah, we had exactly, yeah. Amazon implementing concurrency, and we can see speed ups of like, it takes 3/4 as long to load a page. YouTube, it takes 2/3 as long to load a page, and millions, no, I mean tens or hundreds of millions of people are viewing these pages, and so I mean, I don't know what metric you want to use to illustrate the impact of this. We could do it in tons of CO2 saved, right? It really is a very amazing impact that speeding up, production level code can have, especially on these huge websites. So, why is it hard? Why is concurrency so hard? Why is that bug 7 or 10 or however many years old? Let's look at maybe just one example of why it can be hard, and this idea of data races. So let's say that you're here at the ATM on Green and I can't remember the other street, but there's an ATM on one of the corners of Green, and let's say that you want to withdraw some money. And so to withdraw some money, what you do is you read the balance of your account, you update the balance of your account, or sorry, you subtract the amount, and then you update the balance, right? And so, this is pretty easy. We read the balance. You have $5,000. You are withdrawing $2,000, so now it's 3,000. But before that actually gets updated on the server, right? Before this ATM tells your bank to update it, at the same time, your company is giving you money. They're paying you for the work that you've done. And so at the same time, somewhere else on the world, they read the balance. They increment the balance by this much. And then, and this is kind of the whole idea of concurrency, is because these two systems are happening concurrently, because these two systems are happening concurrently, you can have some real trouble here. And so then the ATM updates the balance, and the computer now thinks that the balance is 3,000. And then, this has already incremented it, and then it says, hey, no, the balance is 9,000 now. And so, luckily for you, you basically just got a free $2,000, and it should be 7,000 instead of 9,000. Now, maybe this happens in the other order, maybe this one happens and this one happens, in which case you just lost $4,000. But we can see how, this implementation of concurrency in a way that, isn't so smart, has led to some serious problems, right? And you might say, okay, yeah, this doesn't happen that often. These two things have to happen at the same time. Well, that's actually not necessarily an uncommon thing, right? Especially with events that are happening hundreds or thousands of times a second. On your computer, these things are happening all the time, and so the chance that two things happen at the same time, and then your program explodes and segfaults, and you get an error and your entire website goes down, there's a non-zero chance, and in fact, it's more of a win instead of an if, probably. So how do we actually prevent this, right? How do we stop this from happening? So as I kind of, have been briefly alluding to, a lot of these challenges of tackling concurrency are solved by ownership, because it removes the idea, or it removes the issue of this thing having the ability to update it and also this thing having the ability to update it, right? In this previous example, both the ATM and I guess, we can say the company have the ability to update the bank account, the true bank account. With ownership, only one of those things can do that at a time. And so what does concurrency look like? Let's talk a little bit about this idea of threads. So when you run a program, of course, a program is just code. You can run a program multiple times, and every time you run it, you spawn a process. Okay? And this process can be made up of threads. A thread is something that is executing code, right? And maybe an example of if you have a program that has two threads is maybe you have one thread that just every second is printing out, hey, this is what's happening. And the other thread's actually doing the work, right? Something like that. So let's read this kind of straight from the Rust textbook. From the Rust textbook, it says, in most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously, and these independent parts are what we call threads. And interestingly enough, in CS241, I think, ECE 391, you actually build this. In fact, after this lecture, I'm going to go work on scheduling for the processes for ECE 391. So maybe you have something to look forward to learning some more about these if this interests you. I think it's 241. I could be wrong about that. I think that covers operating systems. So let's read maybe another example. Yes, Tim. Tim is in my group for ECE 391. So splitting the computation in your program into multiple threads allows us very often to improve the performance because it's able to do multiple things at the same time. But, what if this task has to come after this other task and we're trying to run it at the same time? Well, now we have to build extra code out that handles that complexity. And really the big idea here is you don't know which one's going to happen first. And so you have to sometimes, worry about that and handle it. And let's read maybe one more excerpt together from the textbook. Rust mitigates a lot of these negative effects of using threads and a lot of the pitfalls of using threads, but programming in a multi-threaded context still does take some thought and requires some additional work that is a little bit different than running it in a single thread. Of course, you can't just write code and it have to guess how it's multi-threaded because it's not as good as of guessing as you, right? So how do we create a thread in Rust? Let's look at maybe a first basic example. So what we do is we do thread : spawn. And then inside some curly braces here, we just write code. We write normal code that we want the thread to run. And so let's look at an example. We have our main thread here. And inside of this main thread, we immediately call thread : spawn. And there's some maybe funky syntax here, but let's break it down kind of piece by piece. First, we just give a double bar or two pipes. This is, again, just the syntax. In fact, we'll see, in a little bit that you can put some stuff before here to change the behavior of this a little bit. And then we'll put some curly braces, and inside these curly braces, we just write code. And so our code will be, we'll look at just kind of this indented part, a for loop from 1 to 10. We'll print, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And after each print, we'll sleep for 1 millisecond. Thread sleep just tells the thread to do nothing for a millisecond. Outside of this thread, so we've spawned this thread, and then in our main thread, what we do is we iterate 1 through 5, and we say hi, we print hi number blank from the main thread, and we sleep the main thread for a millisecond. Okay, so what do we think is going to happen here, right? Maybe instinctually you think it's going to print hi number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then hi number 1, 2, 3, 4, 5. But remember, these are threads, and because they're threads, they can execute at the same time. And so, what we get is we can move over here. When we run this, we get hi number 1 from the main thread, so we're here. Hi number 1 from the spawned thread, we're here. Number 2 from the main thread, number 2 from this thread, number 3 from this thread, 4 or 3, 4, 4, and then we stop, right? So, what happened here? Why did we stop? Shouldn't this thread still print out, 6 or 5, 6, 7, 8, 9? Well, maybe it should, but our main thread has ended. Our process has ended, right? We've reached the end of our main, and this thread kind of exists in this, and so we're done. We say we're done. And maybe one thing interesting is because this is a thread, and because these things are happening at the same time, you might not always get the same behavior. And so we can see over here the same code is run. We can see, maybe this time the main thread was running a little bit slowly. And so we can see the spawned thread is able to print 1, 2, 1, 3, 2, 4. It's all over the place. We get all the way to 6 before this main thread ends. And so, maybe, or hopefully, I should say, running the same code 2 times and getting a different result is something that is not great, right? Maybe it's some clear complexity, and let's learn how to maybe tackle that a little bit. Okay, so the first thing that let's figure out is how do we make it so that we guarantee that this thread ends? So the way we do this is we can save the return value of that thread into a variable, and then we call this dot join on the variable. And so let's move over to another code example. Oops. Okay, and let's break down what's happening here. So, our imports, nothing fancy there. Our main function, nothing fancy here. First, we once again do this thread spawn, exact same, 1 to 10, print the number. The only difference is that we're returning from it. So we're going to say let handle equal thread.spawn, or thread spawn, right? So we're just having it return some variable. And we'll call this variable handle because it's kind of like a handler for the thread. And then we'll do our main thread here, our main kind of operations where we're printing these. And then afterwards, we'll call handle join unwrap. Okay, so what does this mean? Really, the important one that I want to kind of bring your attention to is the join, which is saying basically to the main thread, hey, let's wait for this. It's saying, hey, let's wait for this kind of side thread to finish before you continue from here. And so let's run this. We see 1, 1, 2, 2, 3, 3, 4, 4. This part ends, and then we do still see 5, 6, 7, 8, 9. Right? Awesome work. And in fact, we can change this. We can have this take 2 milliseconds, and we'll see 1, 1, 2, 2, 3, 4, 3, 5, 6. Hopefully, maybe this isn't too surprising. We can remove this altogether, in which case we'll see something different. 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And so, this kind of using this dot join and running these different handlers, but also, having the dot join to say, okay, now, make sure we're done with this other thing, suddenly allows us to run two parts in parallel, but also maintain the ability to sync things back up if we need them to be. Right? And so hopefully you can see how this is a pretty powerful tool already, right? We're able to speed, theoretically, this code up by 2/3, basically. Or, wait, did I mess that up? Let's think. No, yeah, 2/3. Because normally, you do 10 milliseconds here and then another 5 here, and instead, we're doing these first 5 at the same time and then another 5, right? And so, just by using threads here, right, basically only a couple lines of code, we're able to speed our code up by 2/3, which is pretty awesome if you ask me. Okay. So yeah, so what this does is we can get a little bit more technical about it. The thread spawn returns this thing called a handler. When we call join on it, it basically just waits for that thread to finish. Okay, and of course, where we're actually waiting does in fact matter. So what happens if we move it from here to here? What do we think is going to happen? Any ideas? Main prints wait for spawn to finish. Main prints wait for spawn to finish. Yeah, I'm not sure what that means. What I think you mean is yeah. So what I think you mean is it's gonna this thread is gonna execute. Oh yeah. The main prints wait for the thread to finish. That's correct. So these print statements here are going to wait for all of these to finish for it to do anything, right? And so kind of effectively, this is almost the exact same of not doing a thread, right? Because we're spawning a thread. It's actually probably worse because you have to have all the extra work of spawning a thread and then immediately waiting for it to end, right? And so we can see, while here we have this nice parallelization, here we do not. And it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4. Very sad. We are now slow again. So, where you put this join, hopefully, clearly matters to you. Let me make sure the bot is set up real quick. Okay. So let's do a quick quiz question. Did I do something wrong, or is the bot down? Oh, yeah, I did something wrong. Okay. Awesome. So, and let's go over this code a little bit while that's there. So let's see what happens. First, we have a function, a main, imports, nothing crazy there. First thing that we're doing is we are spawning a thread that's just going to print thread 1. We will join the handler for that thread, and then we're going to spawn a thread called thread 2. We'll sleep for some amount of time. Excuse me. And then we're going to spawn a thread called thread 3. Then in our main thread, we'll just print main thread. We'll sleep for some amount of time. We'll wait for the second thread to end, and then we'll finish the program. And so let's maybe take a step back and figure out what this is doing at a higher level, right? We're spawning 3 different threads. Inside of each of those threads, we're having them print their statement. We're also printing the main thread. And then we're waiting for the first thread and the second thread to finish. Right? And so, we can start to ask ourselves questions about these. When do we know each one is going to finish? When can we, do we know that the third thread is going to finish it all? Do we know that the second thread is going to finish it all? Do we know by when the second thread is going to finish, right? Is it going to be before or after a certain thing? And so let's kind of go one at a time maybe. So, thread 1, thread 2, thread 3, main thread. Does this work? Well, yeah, it does, right? Because thread 1 starts, thread 1 finishes. That one looks good. Thread 2 starts, we don't know when it's going to start or finish. Let's say it finishes right now. Does that break anything? Nope. Thread 3, and then the main thread. And then, we join handle 2, but we're kind of assuming that it already ran, right? How about this next example? What if thread 2 and thread 3 ran in different orders? Could this be the case? Absolutely, right? Thread 2 is still finished by this point. Maybe, this one took a little bit longer to start up, and so that one's good. What about answer number 3? Could the main thread print before both 2 and 3? Well, yeah, it really could, right? Because maybe both of these, maybe starting a thread happened to take a long time, and then it got to main thread before it got to 2 and 3. And in fact, maybe a fun fact is this is the behavior that we see the most often, is number 3 here. Now, how about number 4? Could main thread print before thread 1? Well, that would mean that we get to this line 22, which is after line 9, which waits for thread 1 to end. And so there's really no possible way for us to be at line 22 and for thread 1 not to be already printed. And so we know, and I'll close the poll at this point, we know that that one probably is not possible. So I'll close the poll in a couple seconds. 5, 4, 3, 2. Okay, so a little bit of split responses here. Some people put 3, and so the big thing to kind of keep in mind with 3 is that this doesn't really break any rules. While it may look weird because main thread is before these two, you have to remember we don't know when these two are going to run, right? With 4 is the correct answer, and the way we can realize that is we know when we get to this line, we know that thread 1 has printed. This is a guarantee that thread 1 has printed. By line 23, it's a guarantee that thread 1 and main thread have printed. And by line 25, it's a guarantee that thread 1, main thread, and thread 2 have been printed. Oh, okay. I try to keep a delay in there just in case, but let me open up another poll just in case you missed it. There. Click on that if you missed the first one. And maybe something interesting is by line 25, we've talked about how we know that the first thread has printed. We know that the main thread has printed. We know that the second thread has printed. But you may have noticed that I didn't say that we know that we don't know that the third thread has finished. And that's true. In fact, the third thread might not print. If it takes maybe an exceptionally long time for this to happen, then it's very possible that this print statement here doesn't get printed. And in fact, if we add a delay there, we will see that behavior. Okay, I'll close this other poll in a sec. Again, if you missed the first one, just click on that and make sure you get attendance in. Okay, and so let's take this a step further, and we're going to be talking about this thing called the move keyword. And this move keyword increases our thread safety even more, and starts to allow us to actually work with variables that we want to be shared in between these. Okay, awesome. Okay, so let's look at a quick code snippet for this. So, hopefully standard at first, some import statements, our main function, we will create a vector of just 1, 2, 3, and we will spawn a thread, and we will give it that vector. And then, we will handle the thread coming back. Now, here's kind of the problem with this, is what if we delete v here, we unallocate v? what happens? So, the big question becomes, if this happens kind of the way we expect it to as a human, V is allocated, V is printed, V is deleted. What's the problem? Well, the problem is that that might not happen, right? This is the whole idea, is that these threads might not happen in the order we think they will. And so what might happen is V is allocated, V is deleted, and then we try to print V. Well, clearly, if you try to print something that is deleted, bad things are going to happen and your computer is going to explode, and so that's probably not a good idea. And so, we really don't know how long that's going to take, and so we really need to make sure that nothing else is using V after the thread. And in fact, we can recall, yeah, we can recall the bank example, right? Here we have two different things, maybe the ATM being this thread, and your company being this, we'll say, main function, both trying to work with the same thing. In the bank example, it was your balance, right? That other server. And in this example, it's the vector. This one is trying to print it, and this one's trying to delete it. And of course, those two things cannot happen at the same time, right? That they can both read it at the same time. That's fine as long as nothing changes it. One can, but once one is reading and one is writing, bad things happen. And especially if both things are writing to it, maybe sometimes even worse things can happen. I won't go too far into that, but bad things can happen. So let's talk about this move keyword. So, you remember how I mentioned that we could put fancy words here and have fancy things happen. Now we're going to put fancy words there and have fancy things happen. And so once again, basically the exact same example, we will create a vector of 1, 2, 3, and the only difference now is we're going to move it to this thread. This thread now owns this vector. And so we actually do not have access to it in our main thread now. If we tried to call drop v, it would say, hey, you can't do that. That's not yours anymore. You don't have permission to do that. And so this allows us to now pass these variables back and forth, have different threads work with it, have different threads, be parallelized as much as possible, as often as possible, and then, when we need it to be secure and we need it to be safe, prevent any bad things from happening and prevent our computer from catching on fire and exploding and burning our entire house down or something. I don't know. Nothing good, for certain. So how do we pass data between threads? There's this way, which passes variables, but what if we want to have it be a little bit more interactive, maybe? Let's talk about this thing called channels. And I think, let me just say, as a quick side note, I think channels are like so cool. This is a concept that I actually run into a lot. And even the same syntax that I run into a lot from like a EE and computer engineering standpoint with like chips having channels to talk to one another. And Rust implements it in a very similar way. And so I just think it's so nifty. And hopefully you do too. But let's explain it. Let's read this excerpt together. So from our Holy Bible, the Rust textbook, one major tool Rust has for accomplishing message sending concurrency is the channel, a programming concept that the standard library provides an implementation of. We can imagine a channel like a channel of water, like a stream or a river, and if we put something in the stream, it will travel downstream to whatever is at the end. Now, maybe one idea that we'll talk about in a little bit some more is you might not be the only person sending things down the river. But there is, and this is an assumption that we have to make, or rather, this is how the implementation is. There is only one person at the end of the river. We'll say there's a waterfall at the end of the river, or maybe a cave. I don't know if, I think rivers flow into caves, right? I mean, how the cave, I don't know anything about geology. I'm sure there is somewhere a river that flows into a cave that formed the cave by erosion. So, anyway, this is a CS class, not a geology class. So a channel has two halves. It has a transmitter and a receiver. A transmitter is where you are putting the boats in the river, and the receiver is where you are receiving the boats. It's the cave, it's the waterfall, it's the person who's catching all the stuff, whatever it is. A transmitter provides the data that we want to save. or that we want to send, and a different part, the receiver, in a different part of code, in a different thread, receives those messages. So how do we actually create a channel? It's actually amazingly easy. So we say let txrx equal mpsc channel. Tx being transmitter, Rx being receiver. MPSC stands for multi-producer, single consumer. In the idea, multi-producer, producers being the multiple people that can put boats in that river, single receiver or single consumer being the single receiver, the only person that's consuming it. And then channel is channel. Channel is channel, right? That's just the function that we're calling to create that. And so let's look at a kind of concrete code example for this. First, our imports, nothing fancy there. Our main function, nothing fancy here, right? Our first line, we say let txrx equal mpsc channel. Once again, multi-producer, single consumer. Tx being transmitter, Rx being receiver. We will spawn a thread. In this move keyword, let me reiterate something, is any values that this thread uses are moved to it. You don't have to specify which values are moved to it. Anything that it's using that are not in its scope are moved into its scope. Okay, so this thread, the code that we want to execute in this thread, we will create a string that says hi, and then we will transmit the value over the channel. And of course, because we have this move keyword, this tx is moved, the ownership is moved into this thread. Wonderful. On the other end, in our main thread, we'll say let the received, stuff be receiver.receive, and then we'll print out what we received. And let's go ahead and run this. And we can see right here, it got high. And in fact, we can make this maybe even a little bit fancier. We'll add the import duration. We'll add a sleep statement. And we'll do this all over again. So let's see, okay, what's happening here? So we print the high, and then we send the high, and then we wait, and we receive the high, and we print this. So, the question is, why are we not getting this high too? Any ideas? So there's kind of two major reasons, right? The first one is we're not necessarily, right, we're kind of reaching the end of our thread here, right? Or we're reaching the end of our main thread here. Caught the first one first? Yeah, so there's two main reasons. As you mentioned, it caught the first one. So this catches this one, right? And then because it caught this one, it's moving on, right? And we reach the end of our thread, and there's no more handling for anything else. And so, if we wanted to have it catch both, what we would need to do is, add another one of these, or, add we can once again do like the let da 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 equal that, and then wait for it there or join it there. But we won't go too far into that because we have other things to talk about. So, these ideas of ownership and these ideas of messaging and moving allow us to kind of make threads in Rust much, much, much more safely. And easily. These examples that we're talking about have only been an addition of something like, 3 or 4 or 5 lines of code, while if you're trying to do the same thing in, C, you could be very sad and have a very bad day. And so let's look a little bit about what's happening here. So what if we try to print the value in this other thread before it happens? As you might have seen, in a second, that's bad. And why is this bad? of course, this is bad because this kind of ties back to the whole idea of ownership, right? We've moved the transmitter into this. This thread owns the transmitter. And similarly, we've moved the val into the receiver. This thread no longer owns val, right? And so when we try to print the value of val, we don't have that anymore. It's not ours, right? This could be writing to it, in which case things explode. you know, like bad things happen. One thing's writing to one thing is writing to the same thing that something else is reading, right? We don't own that anymore. We don't have access to it. It's not ours. And so, one thing when you're doing this in Rust, and really whether or not you're doing this in Rust, if you're doing this in C, if you're doing this in C++, Java, Python, whatever it may be, when you're writing concurrent or parallelizable code, keeping this idea of ownership is actually a super powerful tool. To make sure that you're not going to run into examples where your code breaks, your CPU catches on fire, and your computer explodes, because that's bad. Okay, so how do we take advantage? How can we really leverage the power of the channel, the MPSC? We can clone the transmitter, and so in this example we have one transmitter and one receiver. But of course, as we mentioned, we can have multiple transmitters. And so let's break this code snippet down. We'll open this up. I made a small adjustment here just because the Rust playground was timing out for the other one, which I don't like, and so I made the duration smaller. But let's look at this. So, nothing fancy here. We're importing stuff. We have our main function. We create a channel, same as before, and then we clone our transmitter. And so now we have two transmitters into the same receiver. Let's look at our first thread. The first thing that we're going to do is just make a list or a vector of strings, hi from the thread. And then for each of those strings, we will send the string, and we will wait a little bit of time. Maybe I'll hide this. Well, can't really hide it, but that's fine. At the same time, or maybe before, maybe after, concurrently, we should say, we'll spawn a different thread. This thread will say more messages for you, and it will do the same thing, which is it will send the values over the other transmitter. So this one uses this transmitter, this one uses this transmitter. Of course, why can't these use the same transmitter? Why can't these use the same transmitter? Why can't I put TX in both spots? Click close button. Yeah, it's not worth it. Yeah, I saw Matt. So why can't these use the same transmitter? Exactly. Transmitters, like everything else, right? It's a variable. It's data, right? And so, these are owned too. When you call .send, or maybe you edit the transmitter or send to the transmitter, these are things that cannot happen at multiple times in different spots. And so we need to clone these transmitters. And really another way to think about it, and maybe an easier way, is when we move this transmitter into this thread. We don't have it anymore to move into this thread. It doesn't exist right here. TX1 does not exist on line 24, right? And so maybe if you get into like this whole idea of like this thread, I'm not even gonna get into that. Basically, it's because once again, ownership is the word of the day, I guess, right? And then, kind of the magic part that we'll talk about is we'll say for each received message, we'll print it. And this for each received message, while it's not necessarily perfect, does a pretty good job of handling the stuff like waiting for these threads to finish. So let's go ahead and run this. So again, hi from the thread, more messages for you is the things that the two threads are sending over the messaging channel. So let's see what we got. Hi, more messages from for the EU thread. And so hopefully you can see that we get hi from the thread more messages for you. But because these are parallel and because they are concurrent, they're happening kind of at the same time. And in fact, we can run this multiple times and we'll get a little bit different results. Maybe not every time, but pretty often. Hi more from messages. I don't even know if this one is the same or different. I'm pretty sure this one's different. Maybe it's not. I don't know. But when we run it, we can get different results. And of course, realistically speaking, if we were to change these sleeps, we would get kind of maybe drastically different results sometimes. Sleeps can sometimes unused import. Who cares? Okay, yeah, so this one just makes it so it goes hi from the thread, more messages for you. A big idea of that is it takes a lot less time to send these 4 messages than it takes to spawn and allocate a new thread, right? But, of course, we don't actually know, these threads are already spawned, these are doing other things, and so we can't always assume that. Awesome. So, we now suddenly have this super awesome tool that allows us to speed our code up by a ton, that allows us to have multiple things going on at the same time, to pass data back and forth, to handle passing messages back and forth, to pass, variables back and forth, all this stuff. And again, I really want to kind of harp on the fact that it's not necessarily important that this is happening in Rust. What I really want you to understand is why is this hard? Right? Why is this a hard problem? What can go wrong if one thing is writing and one thing is reading at the same time, right? And maybe how ownership helps us solve that a little bit, right? And luckily in Rust it's all built in, and so we have all this stuff to handle it. But if you're writing in a different language, which you're going to be for other classes, and you're going to be doing some of this similar work in other classes, how can we use this idea of ownership to stop ourselves from writing code that is going to catch our computer on fire or whatever happens, right? Realistically, it's probably just going to yell at you for trying to access stuff that, well, actually, realistically, it won't yell at you, and you just won't know what happened, and it won't work. It will just read data that is incorrect, because you'll assume that it's one thing and it won't be, right? And so, it really lead to some pretty tricky bugs, right? Usually when things crash, sometimes it can be a little bit easier, actually. Okay, so that's about the end of this lecture. Once again, I want to remind you all, take some time to fill out that feedback form. It's for a ton of extra credit. B, it's super, super helpful for us to help us improve the class. We will be releasing it tonight. Yeah, it is the end of lecture, unfortunately. You did kind of miss the whole thing. But I hope that your chem exam went very well. And you can always watch the recording, of course. So fill out the feedback form. Let us know how things are going, and maybe start to prepare your project presentations. Right, it's the last week; they're due by reading day, basically. And so best of luck. I hope that you all have had a wonderful semester, but we'll get more summative on Tuesday on our actual final lecture, and we'll kind of look more generally. Yeah, don't make your computer catch on fires is really the summary of this lecture. Is when you do things fast, your computer catches on fire and explodes. Yep, exactly. Great summary, everybody. All right, well, I'll see you all Tuesday. Thank you all for coming once again, and bye bye.